through. So welcome everybody. Welcome to the fourth Masterclass in the series leading up to the New South Wales Privacy Summit, which will take place on Friday this week. This is of course Privacy Awareness Week, and the Masterclasses are an attempt or an effort to identify major issues related to privacy in not only a highly digital, highly connected world, but also under extraordinary circumstances. My name is Ian Opperman. Let me begin by acknowledging the traditional custodians on the land with which we meet today. Despite the fact that we're all meeting digitally, we are all on land which has traditional custodians. In my case, it's the Gadigal people of the Eora Nation, and I'd like to pay my respects to elders past, present and emerging, and any elders watching today. So we have another excellent masterclass planned for today with three world-class speakers, Stephen Hardy, Wilco Henniker and Alastair Muir. And this is the pointy end of the conversation around the technology for enhancing privacy and technology for use in a hyper-connected digital world. And without any further ado, it's my great pleasure to hand over to Alastair Muir.
Thank you very much. Thank you, Ian. Thank you very much for having us. So my name is Alastair Muir. I'm the CEO of Vantium. We're a Sydney-based consulting business and advisory business. And so we focus predominantly on open data and open banking. So a lot of work within data shares and financial services, but also our clients have included state and federal governments and ASX 20 companies as well. So telcos, banks, insurers, that sort of thing. And so we're a small Australian business, but we do have international partnerships with some of the best in the world in the privacy enhancing techniques space, and include some US companies, some Israeli companies, and obviously some Australian companies. One of our partners, for example, is actually a company called Galois, who are a US-based company that do a lot of work in the defense and intelligence spaces. So they are actually White House advisors and UN advisors in cybersecurity and data privacy as well. So we lean on them a lot for some of that, for some of their expertise. Before I looked at data collaborations and some of the work that I've done with the ASX 20, I've actually also been an advisor to the CSRO. So helping the CSRO specifically with their own program. So helping them to commercialize world-class technology, world-class research. And through that work over the last sort of 4 years, that program has spun out something like 50 companies. And I've been hands-on as a kind of mentor for about 20 to 25 of those companies, all with a kind of a data, AI, and data commercialization sort of focus as well. So that's just a bit of background on me. In terms of going into intros on Stephen Hardy and Wilco, we'll actually let them go into more detail whenever it comes time to their individual parts of the presentation. So I guess just to give a bit of a snapshot and an overview of how we're going to structure this and what we're going to go through, there's actually a lot to cover and obviously in the time that we have. So I'm going to go through the benefits of data sharing at a high level, some of the challenges traditionally to data sharing, some of the traditional trade-offs that are introduced to actually address some of these challenges, plus also a bit of an overview on privacy enhancing techniques or technologies. Sort of the terms can be used interchangeably, and then some real-world applications of where these technologies are used now and in the wild. We're also going to go into the privacy enhancing technologies and the actual how they relate to the 5 safes, which is something I'm sure most of the people on the call will actually be familiar with, that sort of 5 safe framework. We'll also go into some deep dives into differential privacy, homomorphic encryption, multi-party computation, and federated analytics specifically, as these are 4 of the most pertinent areas in privacy enhancing technologies. We're also then going to look at what are the implications of some of these technologies in cybersecurity, and actually also in the drafting of legislation, plus what are some of the other considerations whenever sort of looking at privacy enhancing technologies. I'm going to go into a little bit more information on the regulatory trends around the world, as well as some of the demand and traction we're seeing globally for some of these technologies, and kind of really what a précis of the market is today. And so I'm just going to jump in. So in terms of looking at the actual benefits of data sharing, I mean, really just want to kind of speak at this at a high level. Like obviously we've all signed up for this particular class, this masterclass, so everyone has an interest in some way in sharing data. But I guess the benefits in terms of data sharing really depend on your context or your perspective. So if you're an organization, you may want to get external data sets, a better understanding of your customer. such that you can drive greater personalization of experiences, provide more tailored products and services to your customers, or indeed even to enrich your decision-making systems within your organization. Or you may want to be able to share data with a third-party kind of analytics provider to actually outsource some of the capability or outsource to some of the capability that you don't already have yourself. If you're a government department, being able to implement data matching across data sets across multiple different government departments might actually help in pattern detection and actually identifying things like fraud. You may also want to look at data sharing to deliver social good through evidence-based policy, and I guess there's a global trend that we're seeing towards this being done throughout the world. So a lot of examples in the US, a lot of examples coming out of Europe as well. You may also want to look at how you can deliver better health outcomes as a result of enhanced data. And that leads very much into that kind of healthcare provider world as well, which is with a more holistic view of a patient's healthcare picture. So both treatments, but also what some of their ailments have been in the past. It actually can drive to have healthcare providers and clinicians really drive better clinical diagnosis and actually then better disease detection and prevention as well. It can potentially speed up clinical trials, and it can really really inform a greater body of evidence around potential medical research as well. And then I guess the other kind of perspective that's an important one here is actually the perspective of the individual. So as an individual, whether you're a customer or whether you're a citizen, is actually being able to, from some of those things above, actually drive better health outcomes for you as a patient or a citizen. In the context of organizations, or even how you interface with a government department, say New South Wales Customer Service, for example, how you get enhanced customer experience from some of those additional data sets, and how you get better, more personalized products and services from the organization that you're interfacing with. And then obviously better social outcomes. So if fraud is detected and driven out of the system, then as a taxpayer, hopefully that lessens the burden on you, as well as what we're certainly seeing now with disease prevention and detection and pandemic monitoring as well. So there's some of the benefits to sharing data and why you'd want to do that. I think it's also important here to really focus and talk about the challenges to sharing data. And so certainly there are a number of challenges today as to whether you're a private sector organization or whether you're a public sector organization in terms of going about sharing data or sharing data project. And so I've sort of grouped these into 6 areas. One is privacy, and privacy is key whether or not it's a private sector data share or a public sector data share. So privacy of the consumer or privacy of the citizen. Trust, so this is the trust that exists and the levels of trust that exist between the participants, the people, the participants and parties sharing that data between each other. Then there's commercial sensitivity, which certainly in the private sector, you wouldn't want certain data sets to reveal certain things about your business that may be commercially sensitive. Another area is actually legal and regulatory. So what laws pertain to what data being shared in what context as well. So for example, personal information, there's very stringent requirements around what you can and cannot do with personal information. For example, you're not allowed to share personal information over international borders, for example. Another key aspect here, or a key challenge, is actually around information security. So, we talk a lot about protecting data at rest and data in transit, but actually what we're going to talk about here a little bit also is data in use. So some of the challenges around how do you make sure that whoever actually has access to that data and what they're using it for is exactly what they're supposed to be using it for. And then probably bringing me to the sort of 6th challenge here is actually around the potential ethical and social implications of certain shares in certain contexts as well. And there are plenty of examples potentially in the healthcare industry, and just making sure that you are mindful certainly of those ethical and social implications. So I guess one of the things that this kind of brings us to is actually looking at these trade-offs, if you will, or these tension points between the benefits and the challenges of data sharing. So on the left, we've got the benefits of sharing data. On the right, we've got the potential drawbacks of sharing this data. So you can see that for organizations, they may want to draw on third-party capabilities, or deliver more enhanced customer experience for their customers. However, the risk is that by undertaking data shares with third parties, they may breach privacy regulations, for example, but in the desire to be super personalized, hyper personalized in the experiences, they might actually scare their customers. They might cross that that boundary of the creep factor, not knowing too much about the customer and therefore putting them off in the first place. The same can be said, I suppose, for government institutions or government departments and regulators as well. So on one side, there's the desire to support innovation and competition in the market, but through the use of additional data sets and matching, like identifying potential fraud, and deliver better social outcomes. But on the other side is the real risk around breaches of customer privacy as well. And then, the individual as well. So there may be the desire to access higher quality products and services, but there's the concern about misuse of personal data. So there's these tensions throughout each of the perspectives. So one of the challenges that this then creates is that it means through navigating this, quite often the challenges outweigh the benefits, and actually it means that quite often data sharing and the value through data sharing is actually left uncapturable. And so I think the other, now we just look at this more traditional way of viewing data privacy and security versus data utility and innovation. So and this is kind of why I'm calling it, and we've called it the old paradigm, is that in the old paradigm, the privacy of data and security of data have been on one end of the continuum, and data utility and data innovation have been on the other end of that continuum. And so gradually, what needs to happen to data to manage the risks is that more and more things need to be done to that data. So whether that's fields being masked, values are being removed, data is being de-identified, data is lifted to an aggregate view. As more and more things are done to the data, actually that data becomes less and less useful. And so this is I guess the old paradigm where these two things are almost mutually exclusive. And so this is one of the reasons why we're so excited about privacy enhancing technologies. It actually breaks this old paradigm of you must do something to that data to manage risk. And so that's one of the reasons why we're super excited about it. And we're going to go into more detail on this. And so there used to be only, in this setup, there used to be only three options when it came to sharing data. One is you share with risk. So you have the maximum utility, but you acknowledge that there are a lot of risks there. Two is that you don't share the data at all. Three is that you de-risk but impact the utility of that data. And what we're talking about here with privacy enhancing technologies is that actually those things are no longer required, and it's actually a brand new way to kind of do this as well. So just to go into a bit of information, a bit of detail on what these privacy enhancing technologies actually are. So we've got, and we've named 5 here, but we're only going to go into 4 in detail, for a few reasons, one of them being time. So we've got differential privacy. So differential privacy is where noise is added to the data such that it is impossible to reverse engineer the actual individual inputs to that data. Federated analysis is where parties actually share the insights from the analysis of their data without actually sharing the underlying data itself. And then homomorphic encryption is where data is encrypted before it's shared, such that it can actually be analyzed, but not decoded into its original form. So it's an encryption technique, and this one's a difficult one from my experience for a lot of people to kind of get their head around, is that it's an encryption technique that actually allows for analysis to be performed on the data without it ever being ever readable, the underlying data ever being readable itself. And then zero knowledge proofs is actually where users can prove their knowledge of a value without ever revealing the value itself. Secure multi-party computation is the 5th one. And this allows institutions to conduct analysis on private data held by other institutions without ever having to reveal those inputs themselves. So it's just some very high-level examples of where these technologies are being used in the wild today. So differential privacy was actually used in the United States Census. Federated analysis is actually being used right now, and if anyone's got an Android device, it's actually being used right now. to capture the keystrokes from your actual device, sending an algorithm down to your phone such that that data then doesn't have to go up to the cloud, and so protecting the privacy and the privacy of your keystrokes and what you're entering. Secure multi-party computation and homomorphic encryption. Medco is a company in Switzerland, which is actually a spin out of EPFL in Lausanne, and they use both secure multi-party computation and homomorphic encryption to protect patient records. And so in Switzerland, they're able to, actually hospitals in every canton of Switzerland are actually able to share patient records and clinical information with each other in a way that protects the privacy of the individual and the security of the data. And so that helps to drive better clinical outcomes, but also then helps to inform better outcomes in medical research as well. Then homomorphic encryption, and we're going to go into more detail on all of these. I just wanted to give a sort of a really high level view on it. Homomorphic encryption is actually being used by Microsoft in one of their products called Election Guard, and this is really to guarantee votes in the electoral system as part of election 2020 and make sure that there are the right number of votes and that hasn't been tampered with along the way. Now, Stephen Hardy is going to go into more detail on some of these, and so I just might pass over to you, Stephen, if that's all right.
Sure. I'll try and steal your screen now. While that happens, I'll introduce myself. My name's Stephen Hardy. I'm the CEO of Ambiata, which is a small data sciences company in Sydney. And we do basically a lot of machine learning, AI, and machine learning and AI has huge impacts on privacy, some of which are really still being understood. And so I've been interested for years in the interaction between AI, machine learning, and privacy, and how you can learn from people's data without having to tread over everyone's privacy in doing so. So I'm going to do a couple of deep dives, one on differential privacy and the other on homomorphic encryption. But first, I just try and lay out what we see the problems that privacy-enhancing technologies solve. And I'll also try and map it onto the 5 safes framework, which is quite a popular framework. And I think that quite a few people would like to understand how they interact. So the first part of what I want to talk about is how encryption saves us a lot of trouble when your data's sitting on hard disks and when your data's moving over networks. But when you actually use data, at the moment, encryption doesn't help. Now, the issue there is that when data is going to be used, it has to be decrypted at the moment, and then it's able to be discovered by people and then misused. So that's sort of the sequence of data in use. You can then break that into 2 different parts of the problem when data is used. You've got input privacy. So when something's being calculated on, you put data into the calculation and you get some result out of it. So input privacy is the question of how do you keep the inputs secret, right? So when you're voting, how do you keep your vote secret? Right? If you're making a census, how do you keep the elements of the inputs of the census secret? Right? Now, output privacy is when you calculate something and then you release a result. So when you want to answer a question from the census, say, how do you make sure that that answer doesn't tell something about someone that they don't want to reveal? So input privacy and output privacy. And you can map the technologies that we're going into in this, in those 2 ways. And I'll talk about that in terms of the 5 safes framework.
Stephen, just checking, are you presenting slides?
I am.
We're not seeing anything shared just at this point.
All right, you're just seeing me wave my hands.
It was magical.
It was very good, Stephen.
Right, apologies. Has this come up now?
We're seeing your desktop and your PowerPoint in edit mode.
Yep. So that's at least something. Come on. Here we go. So that was the slide I just talked to everyone. Apologies for that. Input privacy and output privacy. Now, the 5 safes and how this fits. So the 5 safes is a framework that breaks down the use of data in different projects. So you have this notion of a safe project, which asks whether or not the use of data is appropriate. So we're not really going to touch on that in this in this seminar. It also covers off, if you have some data and you want to do something, there are people who are going to access that data. And so that's the safety of people. Can the users be trusted to use the data in an appropriate manner? Another part is, how do you use it? How do you let people access either the outputs or the processing of the data? Is the method of access safe? That's the safe settings. And then it breaks data into two types of data. Safe data, by which it means safe input, and safe outputs, which are when you release some outputs, are they safe? So that's the 5 safes framework. And the pets that we're talking about change this in 3 different ways. The first way is that pets introduce new settings. Right? There are different ways of processing data that change the aspects of the other. So I'm getting a request from someone. Now, those settings change the nature of the other things. So the first one is around input and input privacy. So if you can keep your input data secret, right? So if no one can see what that data is, then by definition, it becomes safe data. It is hidden. No one can see it. It's only through then attacks on outputs or other approaches that you can infer things from data. So that brings us to number 3, which is if the outputs are safer, right? So if we've got ways of improving output safety, then you can do a few other things. One is you can release the data more widely. Right? So that means that you can go to slightly less safe people, or you can reduce the risks of your project inherently, which increase the safety of your project. So this is how it all fits together. But as I said, it doesn't really read on whether or not the purpose of the project is appropriate. You need to have the ethics right, and this is independent of your operation in this regard. Now, next up, I'll talk about the deep dives. Here we go. So I'm going to do a deep dive on differential privacy first. And this is the output safety one. So basically, by making output safer, how you could release data more widely. And the problem context here is the census. Now, a census, very personal data, very detailed, and it's across almost the entire population. The questions you have to ask in terms of output safety is, which statistics do you release, and when and how do you release them? So this is a very real problem. And this is the problem, a lot of text here, but I'll just draw you to the context here is the US Census. So in 2019, the US Census Bureau basically announced that they could take a portion of the publicly released data from the 2010 census and reconstruct individual level records with selected attributes for 219 million individuals. And for that, when they took some external data and tried and matched that up against those individual records, they actually attached names to these records for 52 million people. Now, the Census Bureau is not allowed to release information which is identifiable. So this is a significant issue for the census. And I'm going to introduce differential privacy because this is the approach that the US Census is going to take to stop this from happening in the future. So rather than talk about their overall approach, which is quite complicated, I'll just give you the very simplest version of that. And this is, how you attack a census generally is you do something called a differencing attack. How do you find out individuals' information? So you might ask the census data to tell me the number of people who are over the age of 90 in 2 postcodes who earn more than $100,000. And then you might ask for the same count, but for just one of those postcodes, more than $100,000. And the difference in this scenario is just 1, which means there's one person in the other postcode that has that income. So you could then extend this query by saying, well, tell me how many there are for males and how many there are for females. You get 0 or 1 in that difference, which would tell you the gender, and so on and so on. So by building a sequence of queries against the census, you can work out information about individuals in the census. So that's the general shape of the attacks here that they need to protect against. Now, essentially, this brings you to this utility versus privacy trade-off. So more queries, if you let people ask more and more questions of the census, you get lower privacy because more attacks can be done. And then for low value, but higher privacy, you just restrict the number of queries you can do. And the question is, can you improve this? Now, there's been a lot of work over the years around how you can protect censuses, and differential privacy is sort of the latest in that step. So previously, the things around rounding responses, suppressing small outputs, removing outlying records, all the standard things for trying to ameliorate re-identification. So what we're going to focus on here is the top one, which is adding randomness. So changing the output of the queries to protect people's privacy. So if you take the example I had before, where the first query, the answer was 9, and the second query, the answer was 8, you could add a lot of noise to that. You could say, okay, let's add random numbers between 1 and 20 and subtract random numbers. And you might get 23 for the first output and 3 for the second. So clearly, that's pretty safe. You can't do a differencing attack on that, but it's also not very useful. Then again, you could add just a little noise. And maybe that's useful. Maybe that's useful enough. So it's higher utility, but lower privacy than the case where it's very noisy. So the essence of differential privacy, and this is the differential part in differential privacy, is the amount of noise that you add is tuned to match the difference that happens in the result if you add or subtract a single person. So it's calibrated to the influence of any individual in the original data. So this means that when you get a result and you look at it and go, well, that's 7 and the one next to it is 6. So therefore, I think there's an individual. Well, you can't actually know because both of those numbers have been moved around enough that there's no actual surety that you've identified an individual. Now, I'll say that again because it's sort of the key insight into how differential privacy works. So differential privacy is a property of an algorithm, right? And the algorithm has some noise in it. It changes things. And if you ran it twice for the same query, it would change the result as much as the result would change if you took out any of the records in the group. Right? This means you can't detect the difference in the data, as in the presence of an individual, from the results of the query. Okay, so this came up in about 2008, this idea. Cynthia Dwork from Microsoft Research was the main author on the main paper that introduced it. There's been a lot of work since then, but she alone has 38,000 citations, and that's probably only a quarter of the papers have been published in this area. So a huge amount of effort. Now, going to run back to the census example and talk about what that means for the US Census in 2020. And when you're counting in a census, say you ask for the number of people earning around 500,000 and a given, more than 500,000 in a given postcode, the true answer might be 100. Now, in differential privacy, you essentially add some noise that's drawn from a distribution, and that distribution is what I've shown on the right there. So this is, what's the likelihood that this much noise will be added to the output? And just say you sample from this distribution and you get a 10. That's relatively unlikely to get a 10. Your returned answer is 110. Right? The width of this distribution tells you how much noise you're basically adding. So the question then for differential privacy is, what distribution do you add? How wide should this be? How much noise should you add? And there's a magic number in differential privacy called epsilon. And so people talk about epsilon differential privacy. Epsilon's the magic number. And epsilon tells you how much noise you're adding. Is it a little bit or is it a lot? So if epsilon is small, you're adding a lot of noise. That means that you're not releasing much information. You're not losing much privacy. As you make epsilon bigger, the amount of noise that you're adding gets tighter and tighter. So 0.7, 1.4, about plus or minus 2, it's not so much. So it means that epsilon is characterizing how much noise you're adding and how much privacy you're losing. Now, this is very useful for a particular fact, which is if you did multiple queries here, if you did query 1 and you got a 10, and query 2 and you got a -6, so 94 was the result, and you average them together, you'd get an average answer of 102. So you do one query, you get a certain level of precision. You do 2 queries, you get a better precision. Epsilon's gone up, and in fact, you just add the epsilons to the queries that you've had. What this means is that differential privacy quantifies privacy risk, or the loss of privacy that you incur when you answer a question. Okay, so this begs the question when you go through this is, well, how much can you add? So you add some noise and then you're releasing some data, so you're losing some privacy every time you do answer a query. Now, it turns out that in 2003, which actually motivated quite a lot of this stuff, so mathematicians showed it was possible to reconstruct a database even though there was noise added if you let people do enough queries. Right? Now, you can think about this in the differential privacy sense, is that every time you answer a question, you're giving up a little bit of your epsilon. You're giving up a little bit of your privacy. Right? You've incurring some privacy loss. And they demonstrate an efficient algorithm for executing that attack, which means that essentially, if you can make an unlimited number of queries, you can reconstruct every record in the database, despite whether or not you've added any noise. Now, the US Census Bureau in 2018, as a response to all of the problems they were finding internally, announced that they were going to use differential privacy for exactly that, to overcome the serious vulnerabilities that were exposed by the database reconstruction attack. Now, this was very controversial, and it's very controversial because it changes the nature of what questions a census can answer and how it answers them. So this is this notion of a privacy budget, to say that the Census Bureau is not allowed to release data that pertains to an individual. Therefore, they have to have a maximum amount of privacy that they're willing to lose when they answer questions. And they're using differential privacy so they can measure this. Right? So every query they answer from the census data uses up some of their privacy budget. And essentially what they've said is that when they've run out of budget, when they've used up all the budget that they have that they're willing to use, then you stop answering queries. So at some time in the future, you will not be able to answer any more questions from the 2020 census. Now, this was definitely quite revolutionary, but in the face of this issue that you can reconstruct the database if you don't take such an approach, then we're waiting for other groups to come up with other approaches that can solve this problem without taking such a radical approach. Now, there are a lot of wrinkles to iron out still. I'll give an example of what happens when you use differential privacy on a census. So the Census Bureau released the 2010 census data with differential privacy applied to it so that people could see what would happen. And there's the website I've got up there actually has a whole host of bad outcomes that people identified around using differential privacy that the Census Bureau is now working through to try and make sure that when they do the 2020 census release, it doesn't have these problems. But for example, in the state of Tennessee, sales and use tax revenue gets given to cities based on their sizes. And it's mandated by law that it's based on the sizes represented by the US Census. Now they're going to change the outputs of the US Census using differential privacy, including population counts of towns. So what that would mean on the bottom right here is that different towns, particularly small towns, would get different amounts of funding just randomly due to the differential privacy process. So that's obviously undesirable. On the left-hand side here, we've got the rule that Tennessee school funding relies on the census data products. So these show the number of children of a certain age. Now, if you add a bit of noise to this trail, number of children by age, by district, you're obviously going to get very patchy funding across the school for different school years. So that's also not a really good outcome. So the census team was working hard on trying to fix this now. So that's the census example, trying to illustrate what differential privacy can do. I'll switch now to other uses of differential privacy. One thing is safer data release. In New South Wales a few years ago, 2017, the Opal card data went through a differential privacy process run by Data61 and checked by Melbourne University. And that data was released publicly with the guarantee that you wouldn't be able to get back to an individual's records. Ultimately, there's a company called Privitar in the UK that has a differentially private API on the market where you can basically put it in front of a database and it will add differential privacy to the queries that come out of the database and add up how much privacy you're losing as you're making queries. Now, one of the things about privacy enhancing technologies is they often work together and in unusual ways. As I said, I work in AI and machine learning. One of the great things about differential privacy is it can guard against some interesting things that happen in machine learning and AI, which is if you build a big machine learning model on lots of people's data, the model can learn things about individuals. Now, if you put differential privacy in this training step, where you isolate the training data from the machine learning model using differential privacy, you can guarantee that the model can't learn something about an individual. Now, this is in use by Google and Apple and quite a few others even now. So I'll switch now to the summary of differential privacy. This allows us to release data with quantified levels of privacy loss. It's really the only good way of measuring privacy loss that we have. It's a massive field of study. There's lots of new results. I think the things that the census people are going to, US Census Bureau are going to come out with over the next 6 months will fix a lot of the problems that have been identified in the census. There's lots of activity going on. The thing is, it's not a silver bullet. Applications in the real world still suffer from privacy utility trade-offs because you're adding some noise to the data, but at least we know what we're doing now. We can measure the trade-offs. We can measure how much loss we're incurring when we answer a question. And that's a really significant step forward. Alistair or Wilco, have we had any questions so far that need...
Not as yet, Stephen.
All right. Okay. Well, I might just press on. If you have some questions, I didn't mean to do that. If you have some questions, then please just stick them in the chat and we'll bring them up. We'll save them to the end. I think we've got a good, probably about 20 minutes leeway at the end for Q&A. So that's where that is. Now, I'm going to switch now to homomorphic encryption, which is perhaps even more mathematical than differential privacy. But the aim here is just to give you a flavor of how it works and what it can be used for based on the properties of how it works. So homomorphic encryption is an example of a privacy enhancing technology that hides the input data. That means that you can calculate on things without knowing what they are. And it's called homomorphic encryption because there's a homomorphism, which means there's a mapping, a one-to-one mapping between the encrypted data and the unencrypted data. So basically, if you're doing some operations on your encrypted data, an equivalent operation's happening on the unencrypted version of that data. So you can add up encrypted numbers, and that means that the numbers that you're adding up that have been encrypted are also added up. That's the homomorphic part of homomorphic encryption. What this means in practice is that you can encrypt your input numbers, compute with those encrypted numbers, and then just take the result and only decrypt that. So the rest of it remains secret. Now, why is this a big deal? I talked about this a little earlier. At the moment, you can encrypt things on disk, you decrypt them, and then you do some processing. If someone breaks into the computer after you've decrypted your data, they can steal the data, and they can use it for whatever they want. In the homomorphic encryption systems, data can be encrypted on disk. You can compute on that data, and then you only decrypt the result. So if you separate your compute part from where you hold your decryption key, you've got safety across the entire process of storage, transport, and computation. And that's fundamentally different. Now, there are three types of homomorphic encryption. Partial homomorphic encryption, which lets you either add or multiply numbers. Somewhat homomorphic encryption, which allows a few multiplies and additions. And fully homomorphic encryption, which gives you an arbitrary number of multiplies and adds. So these have different properties in terms of speed and generality. So clearly, as you go down the page, you can do more and more complex things. Unfortunately, as you go down the page, things get slower and slower and slower. So that's a small problem there. What we'll do in terms of an example here is I'm going to talk about voting systems, in particular how to do elections using homomorphic encryption. And that's an application of partial homomorphic encryption. So I just wanted to give you a really simple view of what the mechanism that lets you do homomorphic encryption looks like in this case. Right? And it's pretty much based on, there's a lot of complicated maths behind it, but the fundamental idea in the middle is something that pretty much everyone learned in high school. That is that if we want to encrypt a number m, the encryption of that, that's C here, is related to g to the power of m. It's just an exponent where m is the power. If you take two encryptions and then multiply them together, essentially you're taking the first one, g to the first number, times g to the second number, which we know from standard exponential rules is the same as just adding up the exponents. So if you multiply two of these encryptions together, you get an encryption of the sum of the numbers that we've encrypted. So we can decrypt this and find out what the sum is. If you do this over and over, you can add up lots of numbers. Right? You can just keep on adding numbers. And this is where the vote counting part comes in. Now, this is an article from CNET from earlier in the year, Microsoft's most important product in 2020, if it works. This is called Election Guard, and it's a system for voting that lets voting become completely auditable. So how can homomorphic encryption guard an election? There are actually a couple of things this system does, but two primary ones I'll talk about here. Voters can confirm their votes were properly counted, and anyone can verify that all the recorded votes have been accurately counted. So this is like a transparency mechanism that doesn't give away who voted for who. Right? Now, it's actually based on a combination of privacy-enhancing technologies, homomorphic encryption, zero-knowledge proofs, and secret sharing. And we'll go talk a bit about secret sharing later, but I'll just focus on the homomorphic encryption bit. And again, this is just a sketch. All the details, if you're interested in this, are in the link at the top here, Election Guard specification, which goes into really a great deal of detail into how this works. So this is the sketch. Someone walks into the ballot room and they put something in a touchscreen and it creates an electronic ballot and a physical ballot. The physical ballot gets deposited and the electronic ballot has this homomorphic encryption applied to it. So say in this case, you've got three choices. Each one of these choices for first past the post voting is either a 0 or a 1. And what this system does first is it takes a look at a single ballot and then uses a zero knowledge proof to prove that the sum of the choices equals 1. That is, it's a well-formed vote. Right? And then a hash of this gets added into a system to allow the user, if they want, to check that their vote has been properly counted. Now, when all the voting's been done, all of these homomorphic keys are made, homomorphically encrypted values are made public, and then they're all added up to form this encrypted count for choice 1, an encrypted count for choice 2, an encrypted count for choice 3. These results, just the counts, are then decrypted to form the election results. All of these steps are set up in a way that's verifiable through this combination of zero knowledge proofs and the hashing and the homomorphic encryption. So it gives you a way of adding up all of these secret things, what people voted for, to get the count of votes, which then produces the results. So that's a practical application, one that's in use at the moment. They've trialed this in a couple of elections, I believe, in the US, small ones at the moment. It's not quite ready for 2020, I think, but they're working closely with a lot of election machine manufacturers to try and get them to adopt this protocol for voting. Now, most applications don't involve adding up zeros and ones, right? And so when you have that, you need to use something more complicated, and that's somewhat homomorphic encryption. Now, outside of those special purpose applications, this is what you need. Right? Now, all practical homomorphic encryption schemes at the moment basically use a hard problem as the base of their encryption called ring learning with errors. Now, it's way beyond the scope of this to try and explain how that works. Just going to attempt a very rough sketch just to give you the flavor of it. I'm going out on a limb here, but I'm going to go with it. Now, what I'm showing here is a graphic representation of something called a ring. In fact, it's a polynomial ring. It doesn't really matter. But essentially, in this system, a number is mapped onto an element of this ring, which is a selection of one green dot per circle here. Right? So that's what a number gets mapped onto. It gets mapped from something very small to something quite large. Right? This big polynomial. And in fact, for real applications, these polynomials are huge, very, very big. When you do encryption in one of these somewhat homomorphic encryption schemes, M here is your message. This is the number that you want to encrypt. Right? What you do is you take your public key, which is another one of these ring elements, which masks the message. You add a bit of noise, and you get your encryption. Right? And this is the thing you compute with, this thing which is the combination of your number, your noise, and the public key. Decryption is where you take the private key, that's S, you add it to the encryption in a particular way, and then you take the resulting thing and you round it down to get rid of the noise you added to recover your original number. Right, so that's the process for somewhat homomorphic encryption. That's a bit of a cartoon version. A lot more detail in the blog post that's linked below. But the key thing here is to see that the encryption is just a scaled version of the number you've put in with a bit of noise added and with some masking added. Right? So when you add up two different encryptions of two different numbers, right, they just add up because they're just there by themselves, hidden by this noise and by the mask, the public key mask. Right? You're just adding them up. And similarly with multiplication. And so the entire somewhat homomorphic encryption scheme is a very clever way of getting rid of these masks and this noise when you're doing the decryption step and keeping all the addition and the multiplication working. Now, the reason why it's somewhat homomorphic is because the more things you add up, the bigger this noise gets. And eventually the noise gets so big that this rounding step fails and it decrypts incorrectly. That's why it's somewhat homomorphic. And I won't talk at all about fully homomorphic encryption. So I'll leave that there, but that's the sketch of how these things work. And it's this sort of system that allows you to do much more complicated things. Okay. So what sort of things do they do? Seems to have, okay. So where are they at with the use of homomorphic encryption? I'll just jump into some of the applications briefly. So because we're using somewhat homomorphic encryption, applications basically have to be broad and shallow in terms of their computation. You don't want to have lots and lots of adds and multiplies in a row. You have to keep things broad and shallow. So there have been practical applications in credit score, advertising, privacy preserving advertising. Who would have thought it? Data aggregation, and a few other things. And that's and they work much more efficiently than trying to do something that's very deep. The standardization of this, currently there's a de facto industry standard, but it hasn't yet been adopted by a standards body. It's a little bit of a limitation, but that's coming. And tools and libraries, there are a lot of libraries and tools being developed. There's a lot of interest and activity across academia and industry in this. Microsoft's a big supporter. Satya Nadella came out last year at the Build conference and named privacy and homomorphic encryption as one of their top 3 things, hence Election Guard and the SEAL library and the things that they're doing. So this is really moving forward at pace. There's still some work to go, but I'll just remind why it's so important. It's because it changes the nature of the security of data, and it allows you to do things you might not have otherwise thought you could do. This is my last slide on homomorphic encryption. I just talk about a couple of things where it's in use. The first one is there's actually a local Sydney company called ISUP that has a data sharing platform that uses the Microsoft SEAL library to hide data when they're doing some computation over it. So that's happening here in Sydney, so that's pretty exciting. The Financial Conduct Authority in the UK for the last 2 years has run sort of a giant hackathon, tech sprint, on anti-money laundering, where the challenge is, between countries, between banks, how do you detect illicit money flows, which is a huge $3 trillion problem. And the list of companies I've got down there are the companies that were involved in the homomorphic encryption activities in the last tech sprint. So you can see there's quite a big group. It's all financial services because it's Financial Conduct Authority area. And the final one, another one of these surprising things, is homomorphic encryption in machine learning, back to where I'm particularly interested. So people have demonstrated that you can build neural networks for image classification, for example, that use homomorphic encryption. That lets you either encrypt the data so that you can classify images you don't know what they are, right? Or you can encrypt the network. So you might have some IP, which is a great face recognition algorithm, say, and you don't want to release that. So you can encrypt the network itself and run that over public data. Now, eventually, they'll be able to do both private data and private networks, but that's a little beyond what the state of the art can handle at the moment. So that's it for me for homomorphic encryption. I'll just check if there are any anything out there, guys.
So Stephen, there are quite a few questions that have come through. I might actually just, so some on differential privacy and some on homomorphic encryption. So maybe we just start with the homomorphic encryption ones first. So one from Peter Leonard around, more specifically, I think, Election Guard, is what is wrong with ballot forms and pencils overseen by humans? That said, I understand the US problem, which they introduced through bad technology.
Yeah, so there's nothing wrong with it per se. I mean, it's worked well for many years. Obviously, there have been some specific problems in the US around verifiability of elections, and this addresses exactly those problems. So you might say, well, we don't face those problems, so we don't have to worry about it. I really introduced this as an example of homomorphic encryption at use, addressing a specific and I think very real problem. So hopefully, I think you already knew the answer to that one, Peter, but not much more to add, I think.
Thanks, Stephen. In terms of the another one is, how would you audit Election Guard to make sure it gave the correct results?
Okay, I might have to that's actually quite a big question. They have published a specification, and they published illustrations of all of the techniques and steps used. It's open source code, it's open source specification. So they've invited other, particularly election monitors. There's a group in the US they're working closely with to implement their own verifying software that takes the public assets after the elections happened and runs it through the protocols that they should obey and show that they actually obey them, which then brings you back to the mathematical proof that you've actually added up a set of correct numbers correctly.
Thank you. There's another specific question on the SEAL library. So why is SEAL the best library or set of libraries in your opinion?
It's, in my opinion, it's the easiest one to use. It's pretty much, I take the view of the user often. So as an end user at this point, I think it's the easiest one to use and has the easiest, there are quite a lot of magic numbers in homomorphic encryption schemes. It's sorted out a good set of magic numbers that are easy to use in a convenient way that have reasonable performance. So,
I think, just to add 2 cents to that, I think it's also getting a lot more industry adoption as well. So I think there's a lot more developers and third-party app providers actually building on the SEAL libraries, bearing in mind they only sort of were released, I think 12 months ago, or open source 12 months ago, 18 months ago. They're getting quite a bit of adoption.
Yeah. So cause and effect there, I think.
Yeah.
Yeah.
And I mean, certainly Microsoft are very committed to the development of homomorphic encryption, and they're building it into a lot of products. And I think we're going to talk about that more later in terms of some of the more commercial activities in terms of productization and venture money coming into this space as well. Just looking here, see what other questions we have. Actually, and so David raised the question around the sophistication of the privacy enhancing technologies market generally, and asking the question about, is it reasonable to expect many companies to start putting these types of protections, putting these sorts of protections into use straight away, or do they need an army of data scientists, and are there off-the-shelf products? I might hold that question if that's okay, and then just use that one at the end, because I think that might actually get answered through some of the latter material. And then maybe one specific question for you, Stephen. So a question about neural networks classifying images. While remaining secure and private, I'm still unclear how the classification process can be evaluated to be fair and truly representative of people and ideas represented therein. So this is from Teresa Anderson.
Yeah, so clearly, this is another one of those tension things. People talk a lot about how you should have transparent machine learning. So in terms of fairness, for instance, so this is a great question. For instance, you might want to evaluate the fairness of an algorithm that might bias against people for a particular characteristic that they don't want to reveal. So there's 2 parts to this. One is, if you can encrypt the thing that they don't want to reveal, you can evaluate how biased your algorithm is in terms of whether or not particular subgroups are getting unfair treatment according to your classification. Say you're doing credit scoring and you've got an encrypted network. Right? You still can look at the outputs, they're encrypted. You can multiply them by the characteristic that you want to investigate. You can add those things up and you can get a score, which is, what's the bias of this particular algorithm against this particular protected attribute. Right? The beauty of this sort of approach is that the protected attribute itself remains protected. You don't have to release, even at runtime, what that attribute is, which gives you protection of the attribute and the ability to monitor your system as to whether or not it's being biased to particular subgroups who have that attribute or don't. So I think there's quite a few subtleties around that I'm not really digging into well, but there's quite a lot of opportunity around how you can use these technologies to improve the question of fairness, for instance. Algorithmic transparency overall, when you encrypt things, is problematic, but yeah, that's a pretty big question, which I'm going to hopefully avoid. Yeah.
Maybe one other quick one just on differential privacy, Stephen, and then we'll move on to Wilco, I think. So this is on the noise edition in differential privacy. So is it truly random? For example, if you ask the same question twice, do you get the same answer?
Right. If you so differential privacy is a random mechanism, right? So if you answer the same question twice, you get different answers in the traditional way you set it up. There are systems that apply the differential privacy once, so you basically get a single answer when you ask the same question. Now, that sounds like a good idea. That sounds like, oh, we fixed this problem of averaging. But there's a huge challenge in that, in the sense that you might have a question, tell me the number of people who have, brown hair, okay? I might then ask the question, tell me the number who have brown hair and are men, and the number of people who have brown hair and are women. And I just add up those two answers because one's not quite the opposite now. Sorry, I should have used a different example. But there's a fixed number of gender identifications, and you can add them up, and you add up to the total. So by going through other options, you can always attack this idea that you always answering the question the same way. Right? So that's why, on the whole, differential privacy doesn't even, really, the practical systems out there basically don't adopt that approach.
Thank you. I think will we move on to Wilco,
right.
His presentation?
All right, let me bring the slides up. Okay. Alistair, can you see the slides? Okay, perfect. So I'm Wilco Hennecker. I work at Cyrus Data 61 in the confidential computing group, and I use these privacy enhancing technologies to build solutions as a day job. And the technology I want to show you first is called secure multi-party computation. Come on. Okay. Unfortunately, so we have to be a bit of we have to define terminology a little bit, because often secure multi-party computation is used interchangeably to mean different things. And so for once, it can be an umbrella term for all kinds of protocols between more than one party, which provides some security guarantees and solves a specific problem. And like prominent examples are private set intersection, where you, so several parties have sets of things and they learn what they have in common, but nothing else. And the other one is that I wrote down here is private information retrieval, where you can query a database, but the database does not learn what you actually asked for. And while those protocols are fascinating and very interesting, that's not what I want to talk about today. So I want to talk about SMC as a framework for general purpose computation between multiple parties. And if you think back and how we framed the security promises in the beginning, so this lives in the space of input privacy. It lets you collaboratively share data and analyze data without revealing any inputs. There's to preserve the privacy throughout the computation. So let's start with the promise of SMC. And it says you can compute any function securely by keeping everyone's inputs private. So that's a fairly bold statement, but also a quite useful one, because like it allows you to do compute any function that you can kind of think of with very strict security guarantees. And so if you want to come up with a protocol that achieves those, you have to think about properties that it has to fulfill. And the two most prominent ones are input privacy and correctness. So input privacy just says that every party cannot infer anything about any other party apart from what they can learn by just seeing the output alone. So this is a very strong security guarantee if you think about it. And the other one is correctness. And that just means that if a party is honest, it will not compute an incorrect result. So it either gets a correct result or the protocol will tell them something went wrong. The way they show this is quite beautiful. And so I want to show this to you. So they use what's called the ideal versus real model paradigm. And so if you think about as properties, how you would be able to achieve those in an ideal world, then there's one very obvious solution. You can just say, why don't I invent this trusted party that's always correct? Then everyone just gives the input to this guy, he does this computation and sends back the results. And we can see that all those security properties are fulfilled. Each of those parties only sees their own input and the output, so they cannot infer anything else apart what they can learn from the output. And also the result's always correct. So that's great. However, the real world is not like that. I mean, we want to avoid this trusted third party because that's not actually a real thing in most cases. So instead, those parties have to run some form of protocol, they have to like collaboratively work out the solution to the function. And even worse, some of those parties might actually be corrupt or try and collude and infer more information than they're supposed to. Now, the beautiful thing is with those SMC protocols, the way they show the security is that they show that the protocols emulate this ideal world scenario. And that's what it means. So if you can't tell the real protocol apart from this ideal protocol, then it must be secure, because we just saw that the ideal protocol is secure and fulfills all our properties. And so apart from this beauty, there's also some other advantages to this approach. So one is that it's very general. So you capture all the different commutations you can think of, and you don't have to do any new proofs. It's just given with the system. The other thing is that it's quite easy to grasp the security guarantees. So every one of you can reason about the security of the system, because all you have to do is imagine this ideal world scenario with the trusted third party, and you understand what you get with these protocols. And then another very important point here is also that they allow modular composition. And that means you can compose more complex system by just running several different secure protocols sequentially, and the security will still hold. And if you think about it in a multi-party scenario, that's not always given if you use other technologies. So if you use encryption, for instance, like if you reuse an encryption key, then parties can potentially reuse old encrypted values and inject that in your protocols. And so suddenly you have to reason about all these scenarios, whereas in this framework, it's all given for free to you, to use. So you can build up quite complex systems. Now I want to dive into how this kind of works. And this is all based around the idea of secret sharing. And the way I imagine secret sharing is like with nuclear rockets. And so these missiles are fairly powerful and very destructive. Yes, so the consequences might are serious. And the question is, do you trust any one guy to sit there next to the launch button to just press it at the right moment? And the answers must always, but no. And the way they solve this in the real world is like they spread the responsibility across several persons, and then they either have like different keys that they have to put into the launch panel, or the different passwords. And in secret sharing here, in a secret multi-party computation, we do a similar thing, just with less nuclear fallout. So the idea is you take your secret input, you cut it up in pieces and give every party just a piece of your secret. So if you do that correctly, then none of these parties can learn anything about your secret because they only have a small share. But if they collaborate, they can reconstruct your secret. And a special flavor of the secret sharing schemes is called a threshold secret sharing scheme. And that essentially just means you only need T, but T is smaller than parties to reconstruct a secret. And the way this mathematically can work is shown here. So this is the basic idea of the Sharmir secret sharing. And this is a threshold secret sharing scheme here. So you need 2 secrets out of 3 to reconstruct the secret. This is all based on some basic fact that you need, that if you've got T points somewhere, then they define a polynomial of degree T minus 1. And since I've chosen this T to be 2 in this case, our polynomial is just going to be a line. Now, if you want to create shares of your secret, and the secret I've chose here is 5, this red dot, then what you do, you choose a line that goes through this, has this constant value 5, but you choose a random slope, yeah, any value. The shares then are just this any 3 points on that line, and this I painted them here in magenta. And so you can probably see that if you only got one of those magenta points, you cannot infer any information about a secret because the slope was chosen at random and you have no information about the slope. But as soon as you have 2 of those points, yes, suddenly you can perfectly reconstruct the line and you get the secret back. So that's the fundamental way of sharing your data in secure multi-party computation. But so how can we do arithmetic on those? Yeah. And the way to think about this is you decompose your complex function that you want to compute as a computation circuit. And this can either be on Boolean values, it's just like 2 options, 0 and 1, or you do this on integers. And the way you construct a circuit is like you've got this these arrows here represent shared values, and these boxes are operations. And each operation has like 2 input shares and as output another share. So during the whole computation, data is always a share, and so it's like the security holds. And it also turns out that the pair of addition and multiplication is functionally complete. You can represent any other operation with just those 2 operations. And so you build up whatever you want, and you can think about it as might be quite complex, but you'll get there. You've got full freedom. So the beauty is that we only have to think about how to do an addition and how to do multiplication. So addition is, like in homomorphic encryption, very, very simple because the shares are just polynomials. You could just add them up, and it turns out the addition of the polynomials is the addition of the secrets. Multiplication is a bit harder because, like, if you would multiply shares together, you change the degree of the polynomial and everything gets screwed up. So you have to do something a little bit more complicated. One way of doing is like I've shown here. That's the idea to use random multiplication triples. And so this works in a way that the parties get shares of random values A, B, and C, where C is the product of A and B. So where they come from is not very important. It can either be just a dealer or there are some fancy crypto protocols that generate those. So in the next step, they use those random values to perfectly blind the input values. So if you have a look here, E and D, so what we do, we want to hide X and Y. So we just add these random values to it. And so if you know what like a one-time pad is, that's essentially just you mask the value with some randomness, and there's no way you can take it away unless you know the randomness. So it's perfectly safe to reveal those numbers, and that's exactly what it didn't do. they reconstruct this E and D value, and then you can rewrite the multiplication in like this complicated form. But it turns out that exactly like everything cancels each other out except for what you want to learn. That's the multiplication. Yeah. So what does it give you? So the important takeaway is that you can essentially compute any function in this framework, and it provides you a very holistic view of the security for the whole system. So it's easy to understand what's going to happen, and you can also then build more complex, bigger system by just combining several of those protocols. There's also like, they come in lots of different flavors. So we haven't talked about it yet about security models, but essentially it comes down to reasoning about how powerful your attacker is going to be. And you can think about it in a way that the stronger an attacker is, the more protection mechanism I have to implement, and the more penalty I have to pay in terms of performance. And in secure protocols, there are essentially two ways to measure attacker power. And the one is he allowed to actively change things, or is he just allowed to listen? And the other thing is like, how many parties can he collude with? And you can think of like, if once he colludes with more than the majority of parties, yeah, you have to be quite involved to protect against it. But there are protocols that do that. It sounds all fairly theoretical and mystical. This SMC is actually used in the wild, and I've got a few examples here. There's Unbound, a company in Israel. So they use SMC to protect a cryptographic key. So if you think about the secret key of your web server or your Active Directory, you have to put them somewhere safe, because and that's not always that easy. And you can kind of see how SMC can help here, because once you start spreading this key around in shares in different places, it's a lot harder to steal the whole key. So the next two, share, might, and infer, do similar things, but in a very different way. So they both have provide a platform for processing data. Like you can share your data, do analytics, and machine learning. And so ShareMind solved this in a way that it's got like different computation servers, and you upload your shares to the servers, and then you just ask for some processing results, and for the server do all the work. And in Infer, they just turned it around, so the data never leaves your computer, but as a consequence, you have to do the work. Medco we already saw earlier. It's nice. So they drive better patient outcomes by sharing patient data with different hospitals. And here, the last one is also very interesting. So the Boston Women's Workforce Council, they are interested like in the wage gap, and so they do online surveys for wage gap analysis, and they ask companies in Boston to provide a salary data. And the first time they did it, they only got 38 replies from companies, because they were fairly reluctant to give out this data. But once they started adding SMC technology to this survey platform, suddenly the participation rate increased to 250, and they got a better quality out of the predictions. Yeah. So if you want to try this out yourself, so I suggest having a look at this library called MP Speeds that's developed the Data 61. And the interesting aspect of this library is that it implements a lot of different SMC protocols that vary in security model and also like the type of circuits you can build. And the beautiful aspect of this library is that you describe your problem in a high level language like Python-like, and then you compile it down in all those different protocols, and you can compare them and benchmark them and stuff. Yeah. Okay. So this was the part on secure multi-party computation. And oops, I wanna so the next technique I want to introduce you to is federated analysis. And so when I think about data analysis, I see kind of this in my head, and I'm sorry if I offend anyone. But so in my head, so data analysis is like a funnel where you pour data into the top, and then it gets condensed and processed and distilled until at the end you get like this beautiful drop of insight. So now, if you want to do data analysis on shared data, so the most obvious way to do this is just get a bigger funnel. So everyone comes together, pours their data in, and you get insight as well. And this is great because you can reuse the same tools, the same processes. However, there can be problems though with this data sharing, and we touched on this earlier. So there might just not be enough trust between the parties for this kind of arrangement, or even worse, the data is protected and you're not allowed to do this. So another way of thinking about analysis of shared data is the federated way. And in this way, here everyone has their own funnel, if you will. And so where you keep your data local, you start processing it and condensing it. And then in the federated step, you just work on aggregates. And you still get the same type of insights out. And okay, enough with funnel pictures. Let's jump into an example where we can see how this works in the real world. And so what I want to show you is how Google does this in their keyboard app called Gboard. So as everyone knows probably that like getting data in their phone is really annoying, and like typing is not very nice. And so they tried to add artificial intelligence to the problem of data input. And so they've got two ways. They've got this funny G symbol there, where they try to make suggestions. And the other one is this text prediction. And I want to focus here on the latter one. So text prediction works. So they try to have a machine learning model, and that's a predictor. So how it works is it's essentially just a function. So you give it the last few words that you type, and it spits out the most likely next word you're going to type. And in this case, it spits out the top 3. The challenge is though, so how do you learn such a model? And more precisely, so the challenges that they had is because it's you need a lot of data to get this right, to extract enough information out of user inputs to come up with a good prediction model. And on every phone, there's not that much about, or at least on my phone, there's not much input data. So local learning is probably a bit edgy. But they also want to avoid like a central data story. So if you think about it, the typing history of all Android users, like in one place somewhere on the internet, that's not a nice thought. And so they said, no, they try to avoid this. And the other problem they have with working with phones is they're not always reliable in their internet connection. So you have to account for this as well. But so the solution they came up with is just turning the learning around. So instead of sending all the data to one server, they just do it the other way around. They send model to the data, and then you iteratively improve the model on the device. And so the way that this works, it's pictured here, so they call the algorithm federated averaging. So the setting is that you've got all these phones out there in the wild, millions of them, and there's then one server who acts like as a coordinator that federates this learning process. So here knows the current global model for text prediction, and whenever he wants to improve, he chooses some phones, sends them the model, and then the phone learn on the local data that's on the phone and try to get a better version of the model out. Once the phones are done with learning, it sends it back. The server just adds them all up, like averages those models, and it turns out that it's a better model than before. Now, if we take a step back and think about the privacy implications of this, so is it private? Well, the server does not get any raw data about your typing behavior, so that's great. However, these models are trained on your local data. So every change that you see in the model originates from some behavior of a user, and you can directly attribute this behavior to a user because like you get each of these models individually. So that's probably not a great place to be. And so the first solution they thought about is, well, why don't we use some of these privacy enhancing technologies and this last computation where you just compute a sum? If you can do that in a private way, and this protocol is actually quite beautiful in its simplicity, and so that's why I want to show it to you. So there's this little setup that happens in the beginning. So each phone has to choose and exchange a random value with every other phone. And so you end up with this pairs of phones that each know 2 random values. And the next step, they compute what's called this perturbation value P. And what I want to point you towards here is this strange symmetry between those. So it turns out that the perturbation value of A with respect to the other party, to party C, is just the additive inverse of the perturbation value that C holds. And that's just a fancy way of saying, like, if you add them together, they end up being 0. And that's the trick why this will going to work in the end. So when they run the protocol, each party uses the newly learned model W and adds all the perturbation values onto it. So and this Y value it's then sent to the server. And that's safe to do so because it's essentially, again, this idea of this one-time pad. Because these P values are purely random, the server cannot infer any information about the model itself. However, once the server starts adding all those Y values together, some magic happens. Because if you look at how these Y values were constructed, so he ends up with the sum of all those models, plus this double sum of the perturbation values. And as I just pointed out, for every perturbation value, there's a partner value that's the inverse, so they cancel each other out. And it turns out the whole double sum cancels each other out. It's 0. The server learns the model, everyone's happy. Now, although that's beautiful and simple, it's unfortunately not very practical. So if we go back to the challenges that I faced, phones are not very reliable in their connectivity. And if through this whole process, a phone drops out, then the result of the server will be just random gibberish. So they had to come up with an idea of how to protect from phones that drop out. And the way they do this is with some other idea that we introduced earlier, with secret shares. And how this works is essentially you run the protocol as before, but additionally, those perturbation values that you have to generate, you have to share this with all the other phones. And this way, so this way, it gives the server the ability to remove perturbation values for the dropped-out phones. Now, so now we computed this sum in a secure way. And now, if you reason about the privacy again, so did we do everything that we need to be private? And the answer is again no, because we protected the data during the whole computation process, but not at release time yet. And so, what's the tool of choice that protects outputs? Well, differential privacy. And that's then what I proposed here, to just use differential privacy before you release the models from the phone. And so the interesting bit here is the top two lines. So the black one is just learning without any differential privacy. And the blue line underneath here, this line has like an effective epsilon value of about 1.1 if you use 100 million phones. But that's not unrealistic in this application if you think about how many Android phones are out there. Okay, I have to speed up. So summary. So federated analysis is a great tool to overcome trust and privacy issues. And the important thing to see, and I hope I got across here, is that all those privacy enhancing technologies complement each other. And then we saw it in the example how they used everything out of the toolbox to build this real world thing that's actually running on your phones right now. What the federated analysis brings to the table specifically is that it focuses on aggregates of data instead of the raw form of the data, and that allows you then to scale up to this huge scale, like hundreds of millions of phones, and also has then the opportunity to provide higher utility. And so if you're interested in this technology and want to play with it for yourself, I suggest having a look at OpenMind. So this is an open source community who builds privacy preserving technology. And they have implementations of federated learning, encrypted computation, where both SMC and homomorphic encryption, also differential privacy. There are lots of tutorials and examples on how to use those. So I highly suggest having a look at that. Yes, and this concludes the end of the deep dives. Yeah. And I'll go back to Alistair, I assume.
Thanks so much, Wilco. Sorry, I've just got a call coming in at the same time, which throws everything out. Just give me 1 second, I'll share here. Can you see that okay? Fantastic, Wilco. Thanks. There's actually one question that came in there as you were sort of speaking on the federated analysis piece. Yeah. And the question was, why aren't federated analysis techniques like this used more, I guess, in the industry?
There are, but for one, so it's used at Google. It's also Apple, like when they analyze user behavior on browsers. So there is already adoption there, but I guess the hurdle is that there is no ready-made library for this. It's still early stages. People combine and experiment, but we're getting there. Like if in these examples for SMC I had with the data analysis, they essentially like infer does federated analysis in a way.
Yeah, and I think, from my perspective, I mean, I don't know whether you want to add anything to it, Stephen, as well, but from my perspective, I think it's one of those things where it's it's still that late stage research, early stage commercialization effort. So the maturity isn't there in the technology yet, which requires a bit more bespoke work. Plus, because there's always multiple parties involved in the data shares as well, it actually means it isn't so easy just to get something straight off the shelf. There's a heavy level of configuration work required. And then the more you want to get into the deep mathematics of it, the cryptography skills are also required. So that's just kind of from my experience and perspective on it. Is there anything you wanted to add, Stephen?
No, that's fine. Press on.
All right. So now that everyone's an expert in homomorphic encryption, secure multi-party computation, differential privacy, and we're all fully across privacy enhancing techniques, I thought I'd just go into a little bit of what are the implications of some of these technologies. Implications certainly in this case to data security, or cybersecurity. So traditionally, with cybersecurity best practice would have a focus on data at rest being encrypted and data in transit being encrypted. So between two parties, for example, or multiple parties. But actually now with the likes of privacy enhancing techniques or technologies, it's actually possible to undertake data collaborations without needing to move, disclose, or unencrypt that data. So it actually really solves for some of the problems around data in use. So this kind of there certainly used to be different controls that would need to be put around the data. You need to, as soon as the data left your environment and went to somebody else, you couldn't guarantee that it was actually being used for the things that you had granted permissions for. Whereas this now is something that can actually be solved for through the potential use of the likes of secure multi-party computation, or indeed through homomorphic encryption as well. I think one of the other things that we wanted to touch on was actually, in terms of some of the other implications, it's actually, if we think about data that doesn't need to be disclosed or move, or indeed ever be unencrypted, it's actually, what does this mean to legislation? Because, in one way, legislation needs to be agnostic of technologies and technology models, for example, but it also needs to kind of keep abreast of what the latest technology trends are, such that there's not accidental prescription of out-of-date technology, out-of-date models in legislation. And so some examples of that, I suppose, are, on the left-hand side, there's some words that we've certainly seen where, in legislation that is not aware of some of these technologies, and there's language like move, exchange, etc., or provide to or obtain by, which also seem to preclude the possibility of distributed analytics as well. Now, I'm not a lawyer. I know there are a couple of lawyers on the line, so if any of them would like to make comments or indeed add some flavor to this, by all means, please, that would be great to sort of stimulate that conversation. But there are certainly plenty of examples of this disclosed. And so one example of this is a recent one from sort of late 2019, was actually the Department of Health here proposed, and actually it got passed, as a data matching bill. So the intent of the data matching bill was for Medicare to identify fraudulent Medicare claims. And so the idea of what was to get sensitive data from the Department of Immigration and maybe 5 other government departments, and have a matching effort done across those data sets. But that actually, the way the legislation was written is that all of that data was to move and be centralized with the Department of Health. So obviously, in cybersecurity terms, that's the creation of a honeypot. And I guess it's one of those things where we've seen certain examples, and we were reasonably outspoken about this particular data bill, so we actually put forward a submission to it, and there was actually some press coverage around it as well. But actually, it's one of those things where we certainly see examples where people aren't necessarily aware of some of these technologies and what the actual possibilities are, where you don't need to move data, and that you can write legislation in a different way. And so I contrast that left-hand side with legislation that's drafted without that consideration or knowledge, and with something that we've already touched on, which is the likes of the Boston Women's Workforce Coalition. So this originally started, as Wilco rightly pointed out, as a survey, and it was a way to address the gender pay gap between men and women in the Massachusetts area. But it actually later went on to actually being passed into forming part of a legislation around both measuring the pay gap, but then also addressing that as well. Another example is actually in the US, which is a federal bill on the Right to Know Before You Go Act. So this was really about, using secure multi-party computation, explicitly to get, so a student going to go to a university or enrolling in a university would like to know about the student results and the grades that were attained in each of those universities before they made the decision. And so this was about transparency, but in a way that obviously protected the privacy of the individuals in each of those schools. So this is one where not only the solution was based on secure MPC, but also actually, the legislation drafted to take consideration of that as well. So it can have some pretty serious impacts. And actually there are some examples around the world, and I'll sort of touch on these. And then I'll also, just after this, give you a bit of a feel for what some governments and some regulators around the world are actually doing to proactively embed the use of some of these technologies, plus also think about it from a legislative point of view. I'm just conscious of time as well, so I might have to power through this. So broadly speaking, we're seeing more demand, across the world for the use of these technologies, specifically in financial services. So we're seeing companies in Europe, the US, across APAC as well, also Latin America, use this for fraud detection, for credit scoring, and as Stephen mentioned earlier, regulators are also very interested in the use of these technologies for detecting illicit money flows in financial services, and doing it in a way that means that none of the individual financial institutions actually have to disclose that data to each other, or actually disclose that to the regulator themselves. So they're able to run distributed algorithms, distributed queries, and find out exactly where those illicit money flows are going between banks and even across jurisdictions as well, in a fully privacy preserving manner. And so a couple of examples of people who've invested in this space are Banco Bradesco, BBVA. We've already talked about the Financial Conduct Authority, and actually Austrac are also investing heavily in this space here in Australia. There's also, in other jurisdictions around the world, there's a greater use of some of these technologies. And in some of those things I was mentioning before in data matching exercises. So, detection between multiple departments around tax fraud, so potential fraudulent claims and things, and also the possible detection of wage underpayments as well. We're also seeing a fair increase in regulatory support around the world. So in Singapore, for example, the IMDA actually actively promotes the use of homomorphic encryption and secure multi-party computation for industry data shares, but also for government data shares too. And they've actually published some stuff on this. We've also recently seen that a new data protection agency in the US is going to be created, really to protect consumer data from some of the technology giants is kind of the undertone for it, but also one of their mandates, which is to push privacy enhancing techniques, and specifically homomorphic encryption, multi-party computation. They've also said differential privacy as well. We're also seeing, from a health point of view, we've already spoken about Medco in Switzerland, which is a spin out from EPFL. On the medical research side, NIH, so National Institutes of Health in the US, they're investing about 30 mil into some pretty into privacy preserving technologies, again, MPC, HE focused. University of Texas Health has also actually used it. This is a very interesting one, actually. So they're using homomorphic encryption to protect. So they have an in-home monitoring system for elderly patients. And essentially, they run a bunch of algorithms to kind of see what would constitute a fall before it actually happens in the elderly. And there's obviously naturally, with cameras running, some sensitivity around data privacy there and sort of surveillance worries. So actually, what they do is they build out stick representations of the individual, then send that to the cloud, but it's fully protected by homomorphic encryption, such that queries can be run on those images of stick figures without anybody ever getting the underlying image of the person, and therefore it's fully privacy protecting. They're actually going to be spinning that out as a company very soon. Then from a pure kind of a cyber angle, obviously if you've got encrypted data, that is a pretty proactive protection against malicious exfiltration. So bad actors actually taking that data and releasing it or doing something with it. And then also, I think we've already touched on it many times, the use of secure multi-party computation and distributed analytics, preventing that loss of control, and therefore reducing the threat vectors as well. There are also some really interesting applications in military and intelligence and law enforcement as well. One that I can speak about at a high level is that actually when we were at the Homomorphic Encryption Standards meeting in Seattle in February, we helped a North American intelligence agency with the use of homomorphic encryption to protect their some classified rules that they have on what constitutes a potential cyber threat before it actually is realized. And the idea is that if you can deploy some of these rules on network traffic, you can deploy classified cyber network traffic rules into an unclassified environment. So the idea is you could put it into a corporate environment, you put it into critical infrastructure, you can put it into government networks, and the results are sent back to the intelligence agency. But at the same time, there's no way for those rules to be reverse engineered on the network, for example. So some very interesting applications there for some of these technologies. Just a slide that I'm looking at time and won't be able to go into much detail, but this is essentially what some of the regulators around the world are actually saying about the use of these technologies and are becoming significant proponents of these technologies. On the right-hand side, actually the World Economic Forum have written up quite a good paper on this, and actually this is around the use of privacy-enhancing technologies or techniques in financial services to unlock value. And they've actually coined the phrase here that this represents the next wave of data sharing in financial services. There's also a United Nations Global Working Group on privacy preserving computation, another term or kind of a sub-term of this, and that's under their sort of big data working group as well. Let me just see. So other noteworthy trends, and I think this might talk a little bit about, or a little bit to the question earlier around market maturity and that sort of thing. So, and also just to round out a point Stephen made earlier about standards. So we're definitely seeing more greater levels of standardization across the board. So in the homomorphic encryption standards body, I mean they have a steering committee that's been created a few years ago. They agreed some standards in 2018. In terms of actually getting those standards ratified by external standards bodies, there's now and this is what one of the session was for in February, which is actually to go, who are the first standards bodies we're going to submit this to? And the first one is going to be the United Nations ITU, followed by the IETF and then the IEEE. And so obviously, the move towards standardization in something like HE is absolutely critical for industry adoption as well. Another noteworthy piece there around standards is actually the formation of the MPC Alliance. So this is the Multi-Party Computation Alliance, the global alliance. It's really focused on those who are interested in, so clients who are interested in adoption of multi-party computation, but also vendors who have capability in the space. So we're part of the MPC Alliance. I actually sit on the marketing committee globally for this particular alliance. So it's a really interesting place to sort of see how some of these things pan out. In terms of the commercialization piece, more and more companies are being spun out. You've got Envel, which spun out of the NSA, has raised, I think, 15 million. You've got Infer that spun out of EPFL as well, like also the same place that Medco did. They've raised 15 mil. You've got, this is now on the radars of multiple VCs. And in fact, any VC that's in the cyberspace, large VC that is very much looking at this. Some of the really big ones on the West Coast US have already made their plays. So the likes of Duality, which is another startup in the space that has researchers from MIT, from NJIT, and some guys from RSA as well, have been invested in by the likes of Intel Capital, Team 8, some of the really big guys. Alleged Cyber have invested in Envel. So it's really gaining a lot of traction, and that's kind of consistent with a technology that's kind of in that breakout mode, I suppose is the way to put it. Then specifically around the libraries, we've already touched on some of this. We've touched on Microsoft Seal. There are some others out there as well that are open source, TFHE, Palisades, and then Wilco's already mentioned around OpenMind as well. Sorry that I had to speed through this a little too much. So I think in summary, where originally there was the two ends of a continuum where you've got data privacy on one side, data utility on the other, these technologies really have the possibility to kind of break that continuum, and actually where you can get, there's less mutual exclusivity to the way that data shares can be undertaken. You can get, we've seen it before with some of the public sector ones, where you can get social good without having to put citizen privacy at risk or the security of data at risk. So probably just leave it there. I think maybe then we go to questions if we've got time. Sorry. Do we have any questions come through?
I think you largely covered off the one from Daniela Trainer around federated analysis and why it is more widely in industry earlier. Just some comments, one from Kimberly Weatherall around the legal part, thinking about the way these technologies enable us to avoid breaches of current privacy rules that focused on things like collection, disclosure, personally identified information, but also emphasized to me that current drafting of privacy law and focus on questions like disclosure won't protect people from other things like analysis, personalization, targeting, etc. Because I guess the implication there is that you might enable other ways of doing that don't run foul of the actual, you're not actually collecting data anymore, but maybe the purpose for what it's being used isn't something that's socially acceptable or appropriate. And that's what she says, suggesting the importance of the question that I parked earlier on. Sorry about that, Kim, but it was a bit tricky. None of these mechanisms help us ensure that the purposes of data use aren't appropriate. I just say a general comment. The comment there is these are general purpose technologies and they can be used for lots of purposes. So, they're agnostic as to the purpose. Right?
Yeah, I agree. And I think, we've talked about it before, Stephen, is that these technologies, they should be enabling privacy legislation, not being a way to sort of circumvent it, right? So it should be a way to, you still got the same obligations. You still need to do the right thing from a legislative point of view, but also, from a trust perspective with your customer. It's more about breaking some of those other impediments down as to then fully realizing the value from that data and deliver something better for a customer, deliver something better from an economic value perspective.
Alistair, could I just ask you to stop sharing your screen? We're just looking at ourselves here.
3 copies of ourselves.
Sorry about that. I'm getting used to the technology.
And there was one final question that's just come in from Beth. How would you do legal discovery on data used in this way if there was a dispute? I think the lawyers in the room may be much better qualified to answer that than us. So Peter, Kimberly, a few others there.
If it really works, you shouldn't be able to do it. Because it won't be personal data because there's no way to associate it back to the individual concerned. So is that a problem, or is that a demonstration of the efficacy of what you're proposing? It depends upon your perspective. It does, I guess, raise the other issue of the auditability of the mechanisms that you're using for reliability, but that's a completely different question to the discovery question.
Thanks, Peter. All right, was that Ian, did you have a last word to say? I think we've just about hit time, or Mark?
Sure, there are a couple more questions in the chat, which I'd encourage you to have a look at, one from Daniela and one from David. Thanks, Stephen, for inviting me back in. We are at the point of the evening where if this was a real live presentation in the non-digital world, people would gather around the speakers, pick up a glass of wine, a piece of cheese, and have those in-depth conversations and ask those questions you didn't really want to ask in public. So we're at that point in the digital world. I'm sure if Stephen, Alistair, and Wilco were happy to hang around for a little bit, I'm sure you can ask those questions. You've done amazingly well. We still have quite a few people on this call, on this video session, even though they discovered that the pets here were technologically related as opposed to furry animals. And you've managed to keep people's interest. I've had a few people ask me whether or not they can have a copy of the slides. So I'd really strongly encourage you to share if you're willing to. But folks, I'm going to dial out for my next meeting. So thank you very much for joining. Thank you, Stephen, Alistair and Wilco for a fascinating presentation. And I encourage you all to engage with the speakers, and thank you everyone for your contribution as we lead into the New South Wales Privacy Summit as part of Privacy Awareness Week this week. Thanks very much.
Thanks, Ian. Thanks everyone.
Ian.
For everyone still on the call, I'll shortly post in the chat a link to where you can find all the content that we'll post. So when the gentlemen send me through the content pack, we'll make it available there. And that will also house all of the other content from the other 3 sessions that we've run over the last week as well. I'll have that posted shortly.
All right. I'm just replying in text to some of these questions, but thanks very much for everyone who attended from my side.
Thank you, everyone.
Thanks, everyone.
Yep, so I'll stick around on the chat if there are other questions that people want to ask. But yeah.
Everyone's gone very quiet. Deep in thought.
Hi, it's Therese Anderson here. I was trying to stay quiet in case someone else wanted to speak up.
Go ahead, Therese.
Oh, hi. Just to follow on from the points that were raised, the sticky questions around the not so much the preservation of privacy of the data itself, but the challenges around what actually happens to the data, and the different ways that even if the method itself is agnostic, there are obviously all those challenges in terms of I guess the means that can be exercised upon data. And I come from a position where I think it really has to be a partnership where all the various perspectives can come together on this, but it feels like, at least from where I sit, that is difficult to achieve. And I'd be really interested to hear your thoughts about ways to move forward on that, so that we can work with these new technological capacities to address some of those sticky questions, while also still keeping conversations available to look at the issues that are less solvable by technology at the moment. And those are those classification issues. And I should flag, I'm a trained librarian, so classification will always be the challenge as far as I see.
I might have a little bit of a crack at answering that. The AI guide, so one angle I think about bringing ethicists around this is the overall AI guidelines and frameworks that are being developed at the moment are a collaboration between technologists and ethicists. And one of the guidelines talks a lot about privacy. Right? It's one of the draft 8 guidelines, but other jurisdictions also mention privacy. Yet, I think in some sense, a lot of the technologists involved in the AI space are not really aware of privacy technology. And so that the ethical discussion that's blooming now between AI and ethics is not intersecting, ethics and privacy, or privacy and AI particularly well. So I think around, the Humanizing Machine Intelligence Initiative at ANU, or a few other groups around the Gradient Institute, there'd be the opportunity to draw some, technologists together with ethicists to try and, unpack some of these issues. And I know they've been explored broadly around the world. So it's a fascinating question.
Are there any other questions that we have for Alistair, Wilco, or Stephen? No.
Just down for the last few. Thanks very much, everyone.
So I just want to again thank the three of you gentlemen for a fantastic event tonight. It's very well worth it. We are recording this session, so we'll post these onto YouTube, and I'll communicate the link to that hopefully very, very shortly, along with all the chat and all the data. But again, thank you very much for your time and your knowledge and passing that through to us. It's certainly a very intriguing subject. And I will bid you and our last remaining attendees a good night.
Yeah.
Thank you all.
Thanks, everybody.
Yeah,
Thanks, Mark.
Thanks, guys.